Hello! This lecture is the first lecture where we develop a technique to analyze the data and reach some conclusions based on a sample. So similarly to the univariate case, we can use the hypothesis testing to make some inferences about a mean vector. The test statistic that we used was the t-statistic that had a student's t-distribution with n-1 degrees of freedom. So you can go back and recall how does the test statistic look like. So for example, if our null hypothesis is that mu is equal to mu 0 and our alternative hypothesis is that mu is not equal to mu 0, then we can use our test statistic that looks like, so t is equal to x bar minus mu 0 divided by s, so this is our estimate of the standard deviation, and that is divided by square root of n. In case that we have our population variance, so in case that our sigma is given, instead of s we use sigma, not the estimated value. And here is the sample size. Then, using this test statistic, we derived some confidence interval for the mean. And later, for larger samples, we mentioned the likelihood ratio test and the distribution of -2 ln lambda that had a chi-square distribution. So that conclusion for the univariate tests was based on a normal distribution or a large samples. In our multivariate case, to generalize that t-statistic, we need to assume that our sample comes from a multivariate normal distribution. So here, instead of testing that mu is equal to mu 0 in terms of numbers, we instead test that a vector is equal to some other specific vector mu 0. So we are testing null hypothesis, mu is equal to mu 0, against alternative that it is different. In order to do that, we actually generalize the univariate case and squared our t. We derived another statistic that is called Hotelling t-squared statistic. I suggest you to read the literature to see how to derive the statistic. It is simple. So when testing this null hypothesis against the alternative, we have two cases where we actually have the covariance matrix of our multivariate normal distribution, or when we need to estimate it. So in case when it is known, we already know the distribution of this test statistic and we use this one. However, when we don't know the covariance matrix, then this is when we use our Hotelling t-squared statistic with our estimate of the covariance. What we know for both of those statistics is that under null hypothesis, this test statistic has chi-square distribution, and this one, the Hotelling t-squared statistic, actually, when you multiply it with this constant, it has Fisher distribution with p and n minus p degrees of freedom. This will allow us to use this distribution to test this hypothesis and also later derive our confidence intervals. Let's see first on example how will both of these cases work. So when we have our covariance matrix given and when we need to estimate it. So in order to do that, we will do in Excel. So here, say that we have our covariance matrix given by sigma, so this is our covariance matrix, and that we want to test hypothesis that our mean vector is equal to 70 and 170. First, what we need to say is that we are assuming that the sample comes from multivariate normal distribution, okay, and that we know our sigma as given here. Okay, so let's go to our PDF to see what are we going to do now. So we are testing mu equal to mu 0 against this alternative hypothesis, and which case of those two we have is the first one. So we have given the true covariance matrix. In that case, we will use our test statistic z squared, so this one, that has chi-square distribution, okay, with p degrees of freedom. So we want to use that one. So what we need is our number of observations, our x bar, what we have is mu 0, and inverse of our sigma. So by having all those values, we can compute the value of test statistic, and then based on chi-square distribution, we can make conclusions. So let's go to Excel. First, we need inverse. So inverse of our matrix. Okay, we need to select all. Then we need our estimate of the means, so our averages. Average of the first, so this is x1, and average of the second one. Our number of observation is 14. Okay, we need this but transposed, because we need to substitute this vector. So this is our x bar transposed from this one. We can also write x bar minus mu 0. So this is first one minus the first one, and second one minus second one. So we have our vector. We also need this vector, but transposed, in order to obtain our statistics. So this one, you can always transpose it. You do not need to click right. So this is our x bar minus mu 0 transposed. Okay, so now we have everything to compute our value of z squared, right? So let's see. This is a number, that z squared. It is our, let's go there to see. So it is our test statistic, z squared. So it is going to be some value of test statistic that we are basing our conclusion on. So we are doing the same as in univariate case. We obtain the test statistic value, obtain the critical value of the chi-square distribution, because we know that the test statistic has chi-square distribution, and based if the test statistic value is larger or smaller, or based on p-value, we make a conclusion. So the procedure does not differ from the univariate case in that sense. Just we are using different test statistics. So let's see. Okay, so just again, we have x minus mu 0 transposed times our inverse times x minus mu 0, and in the end times n. So we know that we are getting a number, so we have our n. Okay, so it's 14, but we need matrix multiplication. Then again of our x bar, right? And our sigma to the power of minus 1, and in the end x bar, this one, right? And times 14. So we get a number 5.5498, etc. What we need now is alpha. So say that our alpha, so this is, let's say, given value, or we can choose it, 0.05. Based on that, so this is our z squared. Based on that alpha, we need to find our critical value. So what we know is that it has our test statistic has chi-square distribution with p degrees of freedom. So degrees of freedom is p is equal to, so how many variables do we have? It is 2. Okay, so we can just type here, for example, or about this, chi squared and it is our t squared. We need inverse, so this one is going to return us a left tail. When you write this, you cannot see this on the screen, it says returns the inverse of the left tail probability of the chi-square distribution. So it returns left tail, so this one. What we need to write first is probability. So our probability is 1 minus alpha because it returns left tail. And degrees of freedom is p, which is equal to 2. So we get 5.991. Perhaps the best way to illustrate this is to use GeoGebra. So let's go to GeoGebra. So what we have is 2 degrees of freedom. For 2 degrees of freedom, the chi-square distribution actually looks like this, which is a little bit different than what are you used to. And what we need is our critical value. So this is this one, for alpha 0.05. So our left tail, by left tail, we mean that from the left of our critical value, so to the left of this here number, the probability is 0.95, which means that probability to the right is 0.05 or our alpha. So this is what we need, this value. Based on this value, we can make a conclusion if we should reject or should we not reject the null hypothesis. Basically, what are we asking ourselves? Does the z squared test statistic value falls in this region, so this from 0 to 5.99, or it falls in the region to the right of this number? Our number is 5.55. So 5.55, it's around here. So this means that our test statistic value is smaller than our critical value. Okay, so this means that we do not reject the null hypothesis. Why? Because, for example, when we find 5.5 here, or I can just type it, we see that the probability is 0.937. The p-value is 0.0623. So this is our p-value. Our p-value is larger than our alpha, so we do not reject the null hypothesis. Okay, let's go back to Excel. This is just how it works. Also, there should be a function that returns right tail. So in this case, if you want to add right tail, you need to type 0.05. Okay, and as you see, it returns the same critical value as it should. Just be careful what probabilities you use. Let's see what would happen if we used our t-statistic from univariate case. So for 1 mean, what do we need here is the value of our z-squared statistic, but in this case we need x bar minus mu, okay, so this one, and we need to divide it by square root of our standard deviation. So we know that on diagonal we have a standard deviation, so standard deviation divided by the number, this is 13, the number of observations. In this case, we get our test statistic value for the univariate case for the first one, for the first variable. And let's do the same for the other one. But instead, what we need is this difference and this standard deviation. So this is population standard deviation. Okay. And we also need our critical value. Say that we again use 0.05. And that we test for difference as we did in previous case. So in order to do that, we need inverse for standard normal distribution with probability 0.05, right? Actually, we are testing for difference. So we need probability 0.025, okay, or 0.975, which is the 1 minus alpha, right? So let's see what happens. So for our standard, so 0, 1 is 1.96, our critical value. So as we can see that in one case we reject null hypothesis, and in another case we do not reject the null hypothesis in comparison to our multivariate case. Let's see what happens when we have normal. Okay, so with 0 and 1, and we need this probability to be 0. Okay, 0.95. So what we got is, let's just type 96. Okay, so this is our 1 minus alpha, this is alpha divided by 2, and this is alpha divided by 2. So what we got, our critical values, our values of test statistic is 2.211, so somewhere here, and we got 0.9, so something around here. So in one case we reject, and in another case we do not reject null hypothesis. Okay, let's go back to Excel. So we see our values. So why is that? Because in this case we take in consideration the covariance structure of our multivariate normal sample. So when we compute our z-square statistic, this one, we actually use the sigma into consideration. Okay, let's go to the same problem, but that we are not given the covariance matrix, so instead we need to estimate it. So our covariance matrix is unknown. In that case we use Hotelling t-square statistic. Once again we need our averages. Okay, so those are our averages. Then we need to subtract, in order to obtain our covariance, sample covariance matrix, we need to subtract each observation with respectively the mean. So first, this is x1i minus x1 bar. Okay, so this is the first. Every observation minus this one. And then we need the same, but for second one. So we need this one minus. Don't forget to press F4 to fix the values. This is what we get. And now to obtain our S, okay, so let's say S, we need to multiply. So just from the previous class, multiply transpose matrix, this one, transposed, with this one, okay, so divided by 14 minus 1. Transposed, so this one is transposed. So we get our covariance matrix. This is what we previously done. Don't forget that you do not have to compute these values, but instead you can find S immediately. So just matrix multiply we need transposed, so what? This one, right, minus this one. So this is our matrix that we computed earlier, and again this matrix. So this is a little bit faster way, and we get the same. You do not have to compute this one, but instead immediately compute this directly. Okay, what else we need is our values of the hoteling test statistic. But again, we need our mu0. So we said that this is 70, 170. Then we need the difference, the same as previous. Let's call it for now mu0. Then our x bar is this and this. Then we need their difference. So we need this. Okay. Actually, the opposite. This one minus this one. Now we get our x bar minus mu0. We need this transposed, right? So we can copy the values from this one. To copy the values, you can right click and copy values, or Control C and Control V, but depends what are you using here up. Sometimes you cannot copy if you don't copy values. And then we need our t squared. So what is our t squared? Same as previously. So matrix multiplication, we need it 2 times because we are multiplying 3 matrices. So this one with, now we need inverse. So matrix inverse of S. Okay, and in the end we need this difference, and we get our value of t squared, but we need to multiply it with 14. So this is our value of hoteling t squared statistic. What we know is that this hoteling t squared statistic has Fisher distribution times a constant. First we need to obtain that critical value for what we had alpha 0.05. We need to obtain our f, so critical value, with our degrees of freedom. So this Fisher distribution has p and n minus p degrees of freedom. So in our case it is 2 and n minus 2, so it is 12. Okay, so this is our critical value. Again, Excel has left tail and right tail. So if we do like f, so it is our Fisher, we find inverse, and we want to know what does this inverse return. Excel will always tell you this f and v returns left tail, and there is another one with RT, so this one returns right tail. This one is what we need. So 0.05 degrees of freedom, we have 2 and 12. This is our critical value. But our t-squared statistic does not have Fisher distribution, but we need to multiply it with a constant, with some constant. What is that constant? So we can say this is f. This is n minus 1 p divided by n minus p. So n minus 1, so 14 minus 1 times 2 divided by 14 minus 2. Okay, so this is our value. Sorry, it's actually the opposite. So 14 minus 2 divided by this number, and then we need to multiply it with our t-squared statistic. Yes, but this bracket here. Okay, so this is more like it. So this is our t-squared statistic times that constant that has Fisher's distribution. So we need to compare this value with our critical value. Is it smaller or larger? Based on that, we can make a conclusion if we should reject or we should not reject the null hypothesis that the mean vector is equal to the specific value μ0. You could actually compute the other value, that is when you multiply this constant with what I first wrote, and then compare t-squared with that constant. So let's do the other way. So we basically need 1 divided by this, and we need to multiply this one with this one. So we can compare this and this, or we can compare this and this one. Okay, so we have that our value 2.6, this one, okay, is smaller than our critical value. What does it mean? When it's smaller, we can always go back to GeoGebra for illustration, but now we have Fisher's distribution with 2 and 12. So what we need is 0.05, right? And we need to see if our value, t-squared statistic times the constant, is smaller or larger. If it's smaller, we do not reject. If it's larger, we reject. So we know that our value is 2.6 something. So it is here, so we do not reject the null hypothesis that the mean vector is equal to μ0. Okay. However, if we want to compare the other two values, we can make the same conclusion. So if our t-squared is larger, so let's go back to Excel just to make clear what I mean. If we compare this value and our t-squared statistic value, so if we compare these two, what conclusion can we make? As t-squared statistic is smaller, okay, then we do not reject null hypothesis. If this value is larger than this specific value, then we reject the null hypothesis. So this is basically equal because this is just constant that you can, let's say, move around. Here is the most important to use correct distribution, so Fisher's distribution, because we know the distribution of the constant times our t-squared statistic. In case that we reject the null hypothesis, this means that one of the means, so either this one or this one, differs a lot from what the data may suggest. So it is not supported by the data, our null hypothesis. What we assumed here is that we have a multivariate normal data. However, that can be checked using the QQ plots for the marginal distributions of x1 and x2 and see if they're approximately straight lines, for example. And in that case, when we check this, we can use this procedure to make conclusions. So let's go over again, just quickly. In this case, we had assumption that we have a multivariate normal distribution data, so data from the multivariate normal distribution, with given sigma, so with given covariance matrix and covariance structure. In that case, we use z-squared statistic that has t-squared distribution with p degrees of freedom. And we make some conclusion based on that. Then, in the other case, we theoretically would first check if this follows multivariate normal distribution, but we assume that it does. So for example, using QQ plots, then we need to estimate the covariance matrix as it is not given. So we estimate it using our unbiased estimator that we have proved in previous lectures. Then we compute t-squared statistic and multiply it by a constant that we know that that particular constant times our t-squared, so now statistic, has our Fisher distribution with corresponding p and n minus p degrees of freedom. Based on that, we could construct our test hypothesis that μ is equal to μ0 against the alternative that they differ. So our vectors now, that this vector is equal to this vector. And based on the Fisher distribution and the critical value, we made some conclusions that we either do not reject or reject null hypothesis. So this is basically a summary of what we have done so far. Okay, before going to the confidence intervals for the mean, let's go and solve one more exercise where we have three variables, okay, x1, x2, and x3, based on a sample of 10, where we are given our x bar, our mu0, and our sample covariance matrix. So this is all given, and we need to test hypothesis that mu is equal to our mu0, so our vector mu, and we also assume that our observations, our sample, come from a multivariate normal distribution. So now, because we know that the covariance matrix S, actually sigma, is estimated with S, we know that we need to use Hotelling t-squared statistic, and we know what we'll need. So we need x bar, right? So let's go like this. X bar minus our mu0. We need this transposed, so we can, for example, let's do it another way. So we need this transposed. We need inverse of our matrix, so we need inverse of our matrix S, and we have everything to compute our t-squared statistic. So what we said is that we need to multiply three matrices. So first one is this, right? Then multiply with s to the power of minus 1, and in the end multiply with this one. So we have our value, but we also need to multiply it with n. Don't forget that. Then we need value. So our value is the constant. So not any constant, but our n minus p. It is 10 minus p divided by n minus 1. Let's open 2. N minus 1 times our p. Yes. See? So this one, but we need to multiply it with our t-squared statistic. So what we know is that the distribution of this constant times t-squared. So we need critical value for this value, so Fisher distribution, right? Let's say we again test for alpha 0.05, and this is p, so 3, and n minus p, so 7 degrees of freedom. So we need f inverse. Let's go with right tail. We can always go with left tail, right? So we get our critical value. What we got here is that our value is larger than our critical value, so we reject null hypothesis. Okay. What is interesting with this Hotelling t-squared statistic, among other things, is that we do not need some special tables to find the values of our critical values. we can always use Fisher distribution tables. For example, in previous class we had our correlation coefficient that had a special table, and based on that table we find our critical values. But here we can always use Fisher distribution. So because we are using a software, we do not need to use any tables, and it is much easier. But you would need a table to find this value, and you find it exactly the same way as you did for the univariate case. So this again does not differ, as the conclusions based on these values do not differ from univariate case. This is why we do not pay a lot of attention to these values. Let's move on to the confidence intervals for our mean vector. So let's go here. So what we have here is the distribution of our t-squared, right? So when we know the distribution of some statistic, it is always easy to obtain the confidence intervals, because we know that this probability that this particular value is smaller than our critical value is 1 minus alpha. This is what we also showed in GeoGebra. So the critical values and how does this number behave like. So based on this probability that we know, we can determine the confidence intervals. So just by manipulating this term, we can always find out that the confidence interval for our mean vector will be defined by this one. So this is our ellipse actually. Let's not call it confidence interval, but instead we will call it a confidence region, because now this is a region, not an interval. So from now, instead of referring to it as confidence interval, we will refer to it as confidence region. So from the previous class, we know that this is actually ellipsoid. So our confidence interval for the mean, when we have this normal distribution, is this ellipsoid that is determined for all such values mu that satisfy this inequality. So if we start with our center x, so this is ellipsoid centered in x, then we can find the axes of this, let's call it confidence region or confidence ellipsoids, are this. So plus minus c times, so this is our eigenvalue corresponding to this eigenvector, okay, where our constant c is determined like this. So this is again, we determine confidence c from the fact that this one has Fisher distribution. This is how we find our c. So ellipsoid is centered in x, and the axes of the confidence ellipsoids are this, where c is given as this number here. So square root of our value. Let's see what would be the procedure to find the x's or the coefficients, or what are we finding actually the eigenvalues and eigenvectors. Okay, so say that we have these three variables, assume that they're normally distributed, and what we want to find is the x's, our eigenvalues, eigenvectors, and coefficients, as well as constant c from what we just mentioned. So we can construct, in this case, because this is three-dimensional, you can imagine it as a rugby ball or similar. So in two dimensions it would be just some ellipse that we already plotted in one of the previous classes, with the direction of eigenvectors and our coefficients now depending on Fisher distribution instead of what we previously had, chi squared. So now we had Fisher distribution with particular degrees of freedom. So here we have that n is equal to 20. Then what we need are our averages. So why are we computing this? Because we need our covariance matrix, so the sample covariance matrix. So we can compute it the fast way. So matrix multiplication of, so transposed this minus this times this minus. Okay, so this is the fast way. And in the end we need to multiply it by 19. Not multiply, divide. Okay, so this is our sample covariance matrix. So what we need to do is find eigenvalues and eigenvectors of this matrix. So this is our S. In order to do that, if you're writing by hand, you would need how to compute the eigenvalues and eigenvectors yourself. However, in the first lecture in R, we demonstrated how to compute the eigenvectors and eigenvalues of a simple matrix. So you would need to import it in R and just find eigenvalues. To save time, I will just copy the data. Okay, so this is just imported from R. You would get the same. Just go back to the first lecture. So the first line, what we get are our eigenvalues. Okay, the second line is going to be our first eigenvector. Let's say 1. Then we have, so this is our second. And so this would be our E1 transposed, E2 transposed, and E3 transposed, and corresponding, so this eigenvalue corresponds to this eigenvector, this to this, and this to this one. Okay, so just to make it look a little bit nicer, we would need to, let's transpose them. So transpose this. Okay, I select more than I should. So we have transpose of this. So this is now vectors, our vector. To find our constant C that we need to compute first our Fisher value. So the same way as we did for testing. So let's go like this, 0. Let's say 1. So P is 3, n minus P, 20 minus 3, 17. So we get 2.437. This is our Fp n minus P alpha. Then we need to take square root of this, but multiplied with n minus 1 P. So 19 times P, our P is 3. And then everything divided by n minus P, 17. Let's write it n minus P times P. So we get a value. Okay, so here it's not P, but it should be N, right? Yes, this is not. So this is our constant C. To find the x's, we also need our square root, so square root of our lambdas, so our eigenvalues, times, so multiply with our c. Okay, let's press F4 to the c. So these are our coefficients that we need to multiply with. That we need to multiply with our eigenvectors to obtain the x's. So because we already have our three eigenvectors, we know that, for example, this eigenvector multiply with this one is going to be our first x's. So in both ways, so plus and minus this value, or let's say that this is our length. So just refer, if you don't know what I'm talking about, refer to one of the previous lectures and you will see what actually those numbers represent in geometry. You can imagine that you have only two, so you can see on ellipse how does it look. Okay, but here it is in 3 dimensions. So now we have all values that we need to construct our ellipsoid. So we have our center, so this is our center, this vector. Those are our new axes. So direction of our new axis is determined by these eigenvalues. And this is going to be the length in each way, let's say, of the directions of these eigenvalues. So something like a rugby ball, let's say. So this region is our confidence region. So this ellipsoid. You can always go back to one dimension to get the more intuitive look of this, how this would look, or in 2 dimensions, which is better in this case. So let's summary again. Our center of ellipsoid is given by vector x bar. So this is our center. And let's say half lengths of our major and minor axes in our dimensions. So because we have 3 dimensions, our half lengths of each, let's say, direction of eigenvector e1, e2, and e3 are given by these numbers here. Okay, let's move to simultaneous confidence intervals and Bonferroni confidence intervals. First, let's say that there is a nice result concerning simultaneous confidence intervals that says that if we have a random sample x1 to xn from a multivariate normal population with some sigma positive definite covariance matrix, then simultaneously for all A, so for all A particular interval will contain A prime mu, so A transpose mu, with probability 1 minus alpha. So what does this actually mean to us? That in that particular interval, when we substitute that A with a vector, then on each place it has 1 and 0 on other places, we can actually get the simultaneous confidence interval for mean. So for each mean of x1, x2 to xn. Okay, because when we have a random sample, say of size n, then we have n means. And for each mean, we need a confidence interval. Alright, this theorem tells us because for any choice of A, when we use that confidence interval, we can get actually a simultaneous confidence intervals for our means. Why would we need something like this? Well, the natural, we would like to obtain confidence interval for each mean, but with some simultaneous probabilities. One way to do that is to create for each mean, to create a t confidence interval, so based on the t statistics. So for each mean, one at a time, we create using our univariate case. But then we ignore the covariance structure. And not only that, but when we want for each of these means to have a confidence interval, so based from what we already know, with confidence intervals say alpha, and we have n of those, so probability that all t intervals contain mu e with confidence intervals alpha is actually going to be 1 minus alpha to the power of, in this case, p, because we have p variables. So for each one we have 1 minus alpha probability. So 1 minus alpha times 1 minus alpha times 3 dots 1 minus alpha. And in general, it is smaller, much smaller than 1 minus alpha that we actually want to. So we want the simultaneous confidence to be 1 minus alpha. So for that particular choices of A, we actually take the covariance structure. So this is our covariance structure into consideration. So what I mean, for example, if we choose A, instead of on its place to be 1, we can choose actually A, so this is our vector. We already talked about this. If we take on first and third place to be on first 1, on third minus 1, what we'll actually get is a confidence interval for the difference. So our simultaneous confidence intervals for the difference. mu1 minus mu3. So for any choice of A, we will have this confidence coefficient 1 minus alpha remaining the same for any choice of A. And in general, our one at a time intervals would be narrower, so smaller than our simultaneous confidence interval. So this is just a quick explanation, but I suggest you to read the literature and get back with questions if there are any. So to quickly repeat again. So all our, let's call them t squared, so those are our t squared intervals, that mu1 is between those, mu2 is between those two limits, etc. to mu p, so we have p vectors, all hold simultaneously with confidence coefficient 1 minus alpha, so depending on what we choose. So all of those hold simultaneously. So this is why they are wider, because all at once, so simultaneously, they have this confidence coefficient. Instead of case when we one by one compute them, and we compute each with our confidence alpha, let's say, or 1 minus alpha, then the probability that they simultaneously hold is going to be 1 minus alpha to the power of p, which is much lower probability than 1 minus alpha. So this is why we call them simultaneous confidence intervals. It is easy to compute them. Let's go to Excel. Okay, so we just need to, let's say, put in the formula. So simultaneous. What we have is our xi bar, so this one, minus, so square root of our, so this is our first value, this one is S11 and then we need to multiply it with our square root of p times n minus 1 divided by n minus p times our Fisher, which is this c, so our constant c. Okay, the same we need to do for each of those. So for another one, okay, so this is the lower limit. The upper limit, we just need to basically everything is the same, but we have plus. So this is our upper limit and lower limit. The same way we need to do for our second, so x2, s22, and our c. Right. And for our s3. This is what we get for our lower limits. And for upper, we just need to move everything and type plus. So those are our confidence interval for our first mean. So for mu1, mu2, mu3, and all hold simultaneously with confidence coefficient 1 minus alpha. So those three intervals. This interval contains first, this second, and this third contains the third. We could do the same for the difference, but instead of so we had our S11 divided by n, we will have something else here, because now we need the covariance structure for the difference. And for example, if we had x1 minus x2, so mean, we want confidence interval for the mean mu1 minus mu2, then we would have square root of s11 minus 2 s12 plus s22 divided by n. So this would be our simultaneous confidence intervals for the mean x1 minus x2. So we just need to take another values for the covariance structure. Okay, and let's move to our last, so Bonferroni confidence intervals. So in case when we have small number of individual confidence statements, then we gain control over the overall error rate. So if we want that each of those, let's say, confidence statements have an error of say alpha I, so alpha 1, alpha 2 to alpha m, where m is that number, small number in general, of our individual confidence statements. So in that case, we can create our Bonferroni confidence intervals in that way that probability that all those statements, so confidence statements, are true is greater than 1 minus our errors, so alpha 1, alpha 2 to alpha m. So in that sense, we have control. By choosing that alpha I to be alpha divided by m, because we have m confidence statements, and we have, for example, confidence, we want to obtain confidence of alpha, then we need to divide alpha by each of those confidence statements. So alpha 1 is alpha divided by m, alpha 2 is alpha divided by m. In that sense, when we sum all of alpha 1 to alpha m, we get alpha. So probability that all those statements are true will be greater or equal to 1 minus alpha, which is again simultaneous confidence interval. So all those intervals, okay, contain, so in this case, all these intervals will have simultaneous probability of 1 minus alpha. So the overall, let's say, confidence level is greater than 1 minus alpha by choosing these confidence intervals. So each of our individual confidence intervals, okay, will be alpha I divided by 2. So this is what we would use when we are testing the difference. So we always need to divide it by 2. Usually we divide alpha by 2, but in this case, because we have alpha I, in general it's different, we would need alpha I divided by 2. But when we choose that alpha is particularly, for example, alpha divided by m, then we will have alpha divided by 2m instead of alpha divided by 2, because we want simultaneous confidence interval. Here we have divided by p because we chose to have m confidence statements, but in our case m is equal to p because we have p variables, okay? So for each variable we have mean, so we have p means. So our m would be equal to p in this case. So our p statements are these for I goes from 1 to p. Our m statements that I was talking about. I hope that this is clear. But again, you would have to read the literature. So everything that is mentioned in the preparation before starting the lecture, it would be nice to read so you can follow easy. To compute the Bonferroni, first we need is our critical values. So there we had student t distribution, and we have m is equal to p, so it is equal to 3. We have alpha, so alpha is what we said 0.1. This is what we used earlier, yes, 0.1. So 2p would be 6, right? So because we need alpha divided by 2p, so we need alpha divided by this, by 6. And then we need student. So what we need is inverse, so two-tailed of our probability, and degrees of freedom n minus 1, so 19. So this is our t. Let's call it t19. So this is our critical value. And now we can compute Bonferroni confidence intervals. So we have this minus our t minus 1 and times SII divided by n, actually square root of this. Okay. Okay, so here this is actually, we need not two tails. So this is the left tail, but we need this times minus 1. We need the right tail. Okay, so we actually need this value, not the previous one. This one. Okay, now we can compute. So this here, what we have is our second one and our S22 and our S33. So this is what we get, and also we need our upper limits. but we need plus. Okay. So these are our 90% Bonferroni confidence intervals for our means mu1, mu2, and mu3. In this case, our m is equal to 3 because we have 3 confidence statements, so 1, 2, 3. If we had more, then we would need to here divide by, not by 6. If we had 4, we would need to divide by 2 times 4, this alpha, the one that we want to obtain. And in general, Bonferroni confidence interval are narrower than simultaneous Bonferroni confidence intervals. Okay, what should we note here? That, for example, here we did not divide with square root of n because it is already contained in C, so it is already contained here. And always when we just use the Bonferroni confidence interval for the means, they provide more precise estimates than simultaneous confidence intervals. So when we use for means, as I mentioned earlier, we can use them for example, for difference or for more like linear combinations of our means or similar. So we can choose for simultaneous any a, so any vector, such that you get linear combinations of mu1, mu2, and mu3 because you have a transpose x or a transpose mu, so you actually have that linear combination that you can make a statement about using the theorem. So just a quick summarize about the first part is that we compute eigenvalues and eigenvectors in R. In general, sometimes you might need to compute them by hand, but it is not convenient to do so. Then we import them, so eigenvalues and eigenvectors of S. And then we import them in Excel just to find our constant C as well as this length. And then we just compute simultaneous and Bonferroni confidence intervals using what we previously said. This might be confusing a little bit, so just go over the literature, and if you have any questions, feel free to ask. So this will be it for this lecture. So see you until the next time. Bye.